Hey friends, in this video we're going to talk about patterns that we see in the periodic table. For example, can we tell if an atom of a particular element is larger than an atom of another element based on their positions in the periodic table? What about this? Can we tell how well an atom of a particular element will attract an electron based on its position in the periodic table? And here's another one for you. Can we tell how difficult it will be to pull an electron away from an atom from a particular element based on its position in the periodic table? We're going to talk about those topics and some others right now. You might recall we said in Chapter 5 that the electron cloud around a nucleus in an atom is somewhat fuzzy. It doesn't have a clearly defined edge. So because of that, when we want to determine the size of the atom, we have to use more than one at a time. Here's what I mean. Let's say we want to find the atomic radius of sodium or another metal like sodium. We would need to take a sodium atom and measure the distance between its nucleus and the nucleus of another sodium atom next to it. Then we'd simply take that distance and cut it in half. That's our atomic radius. We can do the same thing with nonmetals as well. If we have two hydrogen atoms that are bonded together, we can find the atomic radius of one hydrogen atom by taking that distance between one nucleus and the next nucleus and cutting in half. So then atomic radius is defined as half the distance between nuclei of atoms that are chemically bonded together. And as I said before, we can see a trend or a pattern in the periodic table with regard to atomic radius. And that's this. As we go from left to right across a period, the atomic radius tends to decrease. Now the reason for that is this. As we go from left to right, we're increasing our amount of protons in the nucleus each time, aren't we? We're also increasing the amount of electrons as well. But since those electrons are still on the same principal energy level, and we're increasing the overall attractions between those electrons and protons, that means those electrons are going to pull in more tightly as we go from left to right. What about if we go down a group? Well, as we go down a group, we see that we are adding principal energy levels each time, aren't we? Since we're adding principal energy levels, we're adding more radius to our atoms, and therefore the size increases as we go down a group. So the overall trend is for the size of the atom to decrease as we go across a period and increase as we go down a group. If you like to keep things consistent in your head, you could say that atoms decrease in size as you go from bottom to top and from left to right. Now sometimes we see that atoms can lose or gain electrons to form these charged particles that we call ions. Atoms that lose electrons form positive ions, and atoms that gain electrons form negative ones. Remember that atoms are generally balanced in the number of protons and electrons they have, but if you're losing electrons, that means that the balance favors the protons, and that atom becomes positively charged. If an atom gains electrons, the balance shifts toward the negative end, and that atom becomes negatively charged. So an ion is an atom or a bonded group of atoms that has a positive or negative charge. Now, how many electrons an atom is going to lose or gain depends upon how close it is to having 8 electrons in its outermost energy level, because an atom feels most stable when it has 8 electrons in that outer level. Metals tend to lose their valence electrons. Take magnesium, for example. Magnesium has 2 valence electrons in its outermost level. But if that magnesium atom will lose those 2 valence electrons, that energy level gives way to yield a nice filled energy level underneath. You get it? Almost like when you get an unpeeled onion and you want to take off that nasty looking outer layer to reveal the nice layer underneath. We can also know how many electrons a metal is going to lose based on how many valence electrons they have. The metals in group 1 are going to lose 1 electron because they have 1 valence electron. Remember, once they lose that electron, they'll have that nice filled shell underneath. Group 2 elements will lose 2 electrons because they have 2 valence electrons to give. Group 13 will lose 3 electrons. You get the idea. So again, metals tend to lose electrons and form positively charged ions. Nonmetals, on the other hand, tend to gain electrons and form negatively charged ions. Take, for example, nitrogen. Nitrogen has 5 valence electrons in its outer shell. Nitrogen will simply gain 3 electrons, thus having 8 in its outer shell. By the way, Each nonmetal in group 15 will take on 3 electrons when they form ions. Nonmetals in group 16 have 6 valence electrons, and so they generally take on 2 more electrons to form their ions, giving them a total of 8 in their outer shell. Each nonmetal in group 17 has 7 valence electrons, and so they simply take on 1 more electron to form their ions. So again, nonmetals gain electrons to form negatively charged ions. Like we said before, metals tend to lose their valence electrons, those outermost electrons. So if they're giving up that outer layer of electrons, they're going to decrease in size, aren't they? They're going to lose some radius. But also, as you lose electrons, you're decreasing the amount of repulsive forces between those electrons, which means they can pack in more tightly toward the nucleus. So losing electrons means you lose radius. Let's use a campfire as an analogy. Here, the people represent the electrons around the atom, and the fire represent... Okay, thank you. Actually get an actual fire here, maybe? How hard is it to light? There we go. Okay, and the fire is the nucleus. Now we can easily see how electrons leaving the atom can actually decrease the size, like so. Yeah, that's kind of creepy. Anyway, you can see now that the group is smaller, just like the atom is smaller when electrons leave. On the other hand, if you gain electrons, you gain radius. Simply put, when you add electrons, you are increasing those repulsive forces, which means those electrons have to spread out a little bit, which means you increase the radius. Let's say we have a smaller group around the fire and a couple of friends arrive to join the rest of the group. Seeing as how everyone needs their personal space, the rest of the group will expand the circle to allow for the newcomers to be a part of the group, giving everyone their own personal space and still having access to the campfire. Isn't that nice? So in the same way, when we add electrons to the atom, it causes the atom's radius to expand, to become larger. So lose electrons, lose radius, gain electrons, gain radius. For our trend in ionic radius then, as we go from left to right, generally speaking, ions decrease in size. There's one thing though I need to point out. Yes, as you go from left to right, those metals are going to lose more and more electrons, aren't they? And it's going to cause that decrease in radius. But when you get to those nonmetals, you'll begin to gain electrons. So there's a jump in ionic size, but again, after that jump, there's a decrease in size because you're not gaining as many electrons as you go from left to right. You get it? So the metallic trend in that period will decrease as you go from left to right, and the non-metallic trend in that period will also decrease going from left to right. Just to show you what I'm talking about, here's a diagram to show the relative sizes of ions going from left to right. You see what I mean? How the metals will decrease in size, but then when you get to the nonmetals, you've gained electrons, they jump up in size, but then begin to decrease again going from left to right. As you go down a group, it's a lot like we said for atomic radius. You're gaining energy levels each time, so therefore your ionic radius increases as you go from top to bottom. To sum it up, the general trend in ionic radius is a lot like atomic radius. Decrease in size as you go from left to right across a period, and increase in size as you go from top to bottom down a group. Or again, if you want to keep it consistent in your head, decrease in bottom to top and decrease from left to right. Now, if you're going to form a positive ion, that means you're going to have to pull an electron away from a neutral atom. There's energy involved in doing that. You see, there's still an attractive force between the electron and that nucleus, and so you're going to have to overcome that energy in order to remove that electron. Ionization energy, then, is the energy required to remove an electron from an atom. So if you have smaller ionization energy, it means you have an atom that's more likely to form a positive ion. In other words, it's easier to pull those electrons away. So the higher ionization energy we have, the less likely it is for that atom to form a positive ion. Group 1 metals have very low ionization energy and tend to form positive ions rather easily. The noble gases, however, have a very high ionization energy. It's very unlikely that you're going to make a positive ion from one of those. If we talk about the first ionization energy of a particular atom, we simply mean the energy that it takes to remove that first electron. The second ionization energy would be the energy required to remove a second electron, and so on. Sodium's first ionization energy is pretty small. It's rather easy to make a positive ion from sodium. But the second ionization energy of sodium is a lot higher. Why is that? Because when sodium loses that valence electron, it has the electron configuration of neon, a noble gas. And as we said, trying to remove an electron from a noble gas is extremely difficult. That's why the second ionization energy of sodium is a lot higher than the first. So we've hinted at it a little bit, but let's talk about the trend in ionization energy. As we go from left to right across a period, ionization energy increases. Remember what we said about atomic radius going from left to right. It decreases, correct? So as you go from left to right, those electrons are going to get pulled more tightly toward that nucleus, more strongly held by that nucleus. So it means it's going to be harder to take an electron away from the atoms as they get smaller and smaller. As we go down a group, we are adding energy levels, remember? So when those atoms get larger and larger and larger, it becomes easier to take away an outermost electron because of what we call electron shielding. In other words, the innermost electrons are kind of shielding the outer ones from the pull of the nucleus. When there's less pull there, less attractive force, it's easier to take an electron away from those atoms. Whereas helium has extremely high ionization energy, francium down here, one of the larger elements, has very low ionization energy. So to sum up, the trend in ionization energy is to increase as you go from left to right and decrease as you go from top to bottom. Or again, you could say increase going from bottom to top and increase going from left to right. If we have a small, close-knit group around our campfire, it's going to be really difficult to get one of those members to leave the group. In the same way, if we have an atom that's small and has a full set of 8 or almost a full set of 8 valence electrons, it's going to be very difficult to pull one of those electrons away. High ionization energy. If we have a large group around the campfire, someone standing on the outside of that group may find it difficult to feel the warmth of the campfire because of all the people shielding him from it. In the same way, electrons on the outside of a large atom may be shielded by the inner electrons from the attractive force of the nucleus, and thereby be easily pulled away from that atom. Low ionization energy. Not all elements are equal when it comes to how attractive they are to electrons. If you have metals, for instance, that tend to give away electrons, well, that's not very attractive to electrons, is it? On the other hand, since nonmetals tend to gain electrons, that would be very attractive to an electron. It wants to go where it's wanted, right? So if you have a chemical bond between a metal and a nonmetal, the electrons tend to flow toward that nonmetal, the one that's more attractive to them. We call this concept electronegativity. It's the relative ability that atoms of a particular element have in attracting electrons while they're in a chemical bond. The units we use for electronegativity are called Paulings, named for scientist Linus Paulings. They range in size from the highest value that's right around 3.98, that's fluorine, all the way down to francium, that has 0.7. So fluorine is the highest electronegative element, and ones like cesium and francium are the least electronegative elements. If you're wondering about the noble gases, we tend to not talk about them in terms of electronegativity much because they form so few compounds. The trend for electronegativity then is that as we go from left to right in a period, electronegativity increases. Remember, as we go from left to right, we decrease in size. That means there'll be more opportunity for those electrons to be attracted to that nucleus. As we go down a group, we get larger and larger in size, which means there's less of an attraction to that nucleus. So we say that as we go down a group, electronegativity decreases. The trend in electronegativity then matches that of ionization energy. As we go from left to right, electronegativity increases. As we go from top to bottom, electronegativity decreases. Or you can say electronegativity increases as you go from bottom to top and from left to right. One last trend has to do with the concept we call electron affinity. Electron affinity describes the energy change that's going to occur when you add an electron to a neutral atom. We tend to think of it in terms of energy being released. Think of it this way. If we have an electron that's really attracted to an element, that means that when it comes together, it's going to release a good deal of energy. Like so. Anytime energy is being released, we give that a negative value, energy going out of the system. So, elements that have greater electron affinity means they're going to have larger negative values of energy. They release more energy when electrons are added. If an element has very low electron affinity, it just simply means there's not a whole lot of energy being given off when an electron is added to that element. If we're talking about noble gases, they don't really form negative ions, do they? So therefore, there's not really any electron affinity to speak of. We find that the trend in electron affinity tends to match that of electronegativity and ionization energy. And that is, as we go from left to right, electron affinity increases. Again, how much energy is released when an electron is added to an atom of that element. It also decreases as we go from top to bottom. So the trend for electron affinity then is an increase as you go from left to right, and we'll say an increase as you go from bottom to top. How about that? Increase going from bottom to top and from left to right. That's all we're doing for this video. Today we talked about trends in the periodic table. The trends of atomic radius, ionic radius, ionization energy, electronegativity, and electron affinity. Hope it's been informative for you, and if I can help you in any way, let me know. In our next chapter, we'll get into a more in-depth discussion of ions. So I hope to see you then. Until next time, God bless.